Invisibly, they hide beneath our feet. For centuries, we didn't even know they existed. But now, they shape our future. They open up amazing possibilities, but at the same time threaten to destroy our environment.
If you look at the periodic table, there's a couple of rows that appear to be kind of kicked out. They don't quite fit in there, and they're down at the bottom, and people tend to ignore them.
The reason why we started focusing on them is that they have a number of very exciting technological properties. Their essential characteristic is that they stick together like glue. It's actually very difficult to pry them apart.
When I think about it, I view them as being catalysts for future development in the 21st century. No real development is going to happen without them.
In here simmers the hope for a bright future. Chemical elements considered useless for a long time. Their properties were simply too weird. Only a few years ago, researchers discovered their true value, and that triggered a technological revolution. Today, they are more valuable than oil or gold. Rare earth metals.
These elements are considered rare because they were very difficult to chemically isolate. But once isolated, they have properties that allow a myriad of modern technologies.
Smartphones and tablet computers, hybrid cars and electric vehicles. All our modern gadgets contain rare earths. Baotou, China, the world's largest rare earth mine. 97% of the world's supply of rare earths is mined in China.
Apart from promethium, which is very scarce, all the other rare earth elements can be found in China. And when you talk about rare earths at the moment, you automatically talk about the resources in China.
The open-cast pit at Baotou is in fact an iron ore mine. It started production in 1927. For decades, rare earths were considered a waste product, until prices began to rise on the world market.
A couple of decades ago, the Chinese discovered that the material which was above iron ore in a place in Inner Mongolia was in fact rare earth ore, and that they could, from this material that had been dug up and cast aside, they could separate rare earths. And they started producing unseparated rare earth oxides.
So has China become the world market leader only by chance? The head of the Chinese Society for Rare Earths thinks differently.
In the 50s, China began the exploration of rare earths. In the 60s, we built our own processing system and began mining operations. In the 80s and 90s, we started mass production.
No doubt. By now, we all depend on China. Rare earths mined and refined in China with dirty and outdated methods are bought by high-tech companies around the world to produce smartphones, electric cars, and wind turbines. Matthias Buchert from the Institute for Applied Ecology in Darmstadt knows how difficult it is to produce rare earths.
You have to bear in mind that rare earths never occur on their own, but always in groups. They're chemically very similar. To separate them, you need very sophisticated processes that need lots of chemicals and energy. Only then you end up with the pure elements or metals.
Bremen, Germany. Rare earths are already in short supply, and they're expensive. Global consumption has doubled during the past 20 years and is still rising steeply. Therefore, researchers are looking for new deposits around the world. Andrea Koscinski from the Institute of Geochemistry investigates rare earth deposits in the Pacific Ocean. She's particularly interested in these strange nodules, which are full of useful raw materials.
There's a demand for raw materials and there are deposits on land, but many natural deposits are in remote, sensitive ecosystems. In the rainforest, for example, or in coastal areas, or they're mined in countries where people are working under inhuman conditions. All these things could be avoided with deep-sea mining.
Hawaii. In the port of Honolulu, a research ship sets sail. On board, scientists searching for rare earths.
We've known for some time that manganese nodules and manganese crusts on the ocean floor have a relatively high metal content, especially nickel, cobalt and zinc. But due to new technologies like green energy generation and so on, the demand for rare earths is rising, and we're now more interested in these elements because of their economic value.
Diving robots are scouring the seabed for manganese nodules. Since 2006, the German Federal Institute for Geosciences and Natural Resources has been exploring 2 sites in the Pacific Ocean. A video camera shows images of the ocean floor. But is it really so easy to simply pick up natural resources from the seabed? Environmentalists are worried about the destruction of the ocean floor.
There are quite complex life forms down there, and processes in the deep sea are very, very slow. Everything grows and regenerates slowly. So if we interfere with such a system, it's difficult to predict how long it will take before it regenerates.
Scientists hope to find millions of tons of rare earths in the Pacific, enough to make us independent of China's supplies.
This is an area of research we've only just started to explore, but we already feel that it'll have a much greater importance in the future. This is one of our big challenges. If we want to harvest these nodules, how do we get the raw materials out of them? For example, rare earths.
Andrea Koscinski wants to find out what's hidden inside these manganese nodules and how to get it out.
Und die sieht gleichmäßig gewachsen.
Genau, es sieht gleichmäßiger aus. Ja. Der Kern ist auch wirklich hier in der Mitte. Ja. Da sieht man eigentlich sehr schön.
You can see here that both these manganese nodules have a core. They need some kind of seed to start growing. This seed, like this little stone here in the middle, just sits somewhere on the seabed, in the sediment, at a depth of 4,000 or 5,000 meters. It could be a fragment of a rock, or a fish tooth, And deep down there, where this seed is, chemical processes start depositing this black material, manganese and iron oxide, around this inner core here.
But what exactly is this little nodule made of that took millions of years to grow on the ocean floor?
We focus on high-tech elements like rare earths, for example, but we also look at the entire spectrum of elements to get an idea of the makeup. If you want to extract rare earths, you have to get them out of this black material first. There are no distinct lumps of rare earth minerals that you can simply pick out mechanically. It's a compound. We have to understand first what this black stuff is made of. Only then can we develop methods to pick out certain elements.
Analyses show that manganese nodules contain high amounts of rare earths, raw materials that are urgently needed for the green technologies of the future. But is it okay to ransack our oceans to produce solar panels, electric cars and wind turbines? How green is our future if we have to destroy pristine ecosystems?
You have to consider that there are many countries in the world that still have some way to go to build an infrastructure for an adequate standard of living. And if these countries are to use green technologies to get there, then they need new resources, like, for example, rare earths.
To build more wind turbines and solar energy plants around the world, we have to exploit new rare earth deposits. The difficulty is finding them in the first place.
Für die meisten Metalle, mit denen wir im täglichen Leben zu tun haben,
For metals like iron, chromium, zinc, lead, copper and so on, there are very specific deposits. So we have zinc deposits, we have lead deposits, well-defined structures from which we can easily obtain the metals. This is not the case with rare earths.
Das ist bei den seltenen Erden überhaupt nicht der Fall.
Right in the middle of a cornfield in Saxony, geologists follow a hot lead. During GDR times, scientists were looking for uranium here, but instead they found rare earths. Nobody was interested in these strange elements back then, so the mine shaft was closed. But now a mining company is test drilling again, hoping to tap into the largest deposit of rare earths in Europe.
If you're looking for investors and you tell them, we have some GDR documents, then most investors will say, well, yes, but they were written during the socialist GDR period, so we don't really trust them. This means we need to reconfirm the old data.
Geologists drill deep into the rock. 4.4 million tons of ore are supposed to be here. A blessing for the German high-tech industry, which is completely dependent on rare earth imports from abroad. But how to excavate the treasure? A huge open-pit mine in the middle of Germany is not an option.
This rare earth deposit has a diameter of 130 meters and a depth of 1,000 meters. This would make a gigantic hole. We can't do this. Our best option is to build an underground mine shaft. This means we only need a deep pit with a small tower at the surface and a few buildings around it. The entire mining operation would happen underground.
An expensive, technically complex deep mining shaft for a tiny deposit. Is this economically viable? The data from the test drilling needs to determine the concentration of rare earths in the ore. To the naked eye, they are invisible.
Gold sparkles beautifully. Diamonds can also be seen easily. As for rare earths, they're very inconspicuous. This stuff looks like cement. It's grey and nothing sparkles. Nothing catches the eye. We only know from geochemical analyses that there are rare earths in here. Knowing that, we can of course look at the samples and say, yes, rare earths are in fact present. But we can't see them with the naked eye.
Neodymium makes magnets stronger. Yttrium ensures vivid colors on computer screens. And lanthanum makes electric car batteries more efficient. But for a long time, scientists simply didn't know what to do with these strangely named chemical elements. Cerium, for example, was discovered in 1803, but it took more than 100 years until an inventor came up with a bright idea of what to do with it.
Die ersten Anwendungen der seltenen Erden waren im Wesentlichen beschränkt auf das Element Cer. Es gab zwei Anwendungen, ganz
The first applications for rare earths were essentially limited to the element cerium. There were two applications. One was using it for lighter flints, and the other one was making incandescent mantles for gas lamps out of it. This was basically the reason why people mined rare earths at all.
Later, other applications were found for rare earths. Lanthanum, for example, made the production of gasoline much easier and cheaper.
Wenn wir uns den Benzinpreis in Deutschland zum Beispiel anschauen,
the price of gasoline would probably be between 10 and 30% higher than what it is right now if it wasn't for rare earths. And it's already quite high.
obwohl ja schon hoch ist.
Mountain Pass, California. Long before China, the US was the main producer of rare earths.
A lot of people ask the question of, where do you find rare earths? And the simple answer to this is you can find them in your backyard. It's just that the concentration is so low you could never get it out. The trick is finding deposits of rare earths that are rich and large.
For decades, the mine at Mountain Pass was considered the most important rare earth deposit in the world.
The start of the Mountain Pass district was in about 1949 when prospectors found a radioactive signature on some outcropping of rock. They analyzed it and found that it was a remarkably rich ore of rare earth minerals.
The problem with deposits like Mountain Pass is that rare earth elements are usually closely bound to other elements. Many of these contaminants are radioactive. To isolate rare earths, mining companies use sulfuric acid, nitric acid, and hydrochloric acid. This produces highly toxic radioactive effluents. The reason why rare earths do not exist as individual elements in nature lies in the geological formation of the deposits.
The geologists tell us that there were 8 volcanic intrusions in which molten carbonatite rock came up through that crack and then just deposited in layers one after another and built up the whole deposit.
Between 1965 and 1995, the mine at Mountain Pass was the world's largest producer of rare earths. The raw materials were needed for making lighters, gas lamps, color television sets, and for producing gasoline. However, the production processes at Mountain Pass were complicated and prone to failure. In 1998, the worst-case scenario happened. 1 billion liters of radioactive and chemically contaminated wastewater leaked from a collecting pond and polluted a nature reserve. Stricter environmental regulations made the mine unprofitable. In 2002, Mountain Pass closed.
Note that you already have a meeting about budgets at 12 p.m. Shall I schedule this anyway?
Move it to 2.
Shortly after the closing of Mountain Pass, a technological revolution happened. Smartphones and flat screens took the world by storm. At the same time, environmentally friendly cars and alternative energy sources became popular. All these modern technologies need rare earths.
Wir sind gegenwärtig 7 Milliarden Menschen. Wir werden in 40 Jahren
We're currently 7 billion people. In 40 years, we'll have an additional 2 to 3 billion. These people need resources, not only food and drinking water, but also rare earth metals, which are used in mobile phones or cars or wind turbines. This means that the demand for raw materials will increase tremendously in the future.
Beijing, China. At the same time as the Americans withdraw from the rare earths business, the Chinese take over. The new economic superpower is able to produce raw materials and finished products at dumping prices. In China's boomtowns, skyscrapers are mushrooming, and the domestic demand for consumer goods is rising. For example, China has the largest number of mobile phone users worldwide. As demand for smartphones and flat panel displays rises, China's production of rare earths increases accordingly. One by one, mines in other countries close down, unable to compete with China. The world is now almost entirely dependent on China's rare earths.
In den letzten 10-15 Jahren hat China immer mehr die großen Anteile.
During the last 10 to 15 years, China has taken over not only mining operations, but also the separation and production of refined rare earths. Around 97% of all rare earths are now produced in China. They are in a very dominant position. But in 2011, China's government suddenly restricts its rare earths exports. The mines reduce their output accordingly. The world gets a feel of how powerful China has become. Because prices shoot up on the world market, energy-saving light bulbs, for example, suddenly get 25% more expensive.
The problem of the reduced exports from China really is one that's been in the making for a long time. China reduced the exports for a number of reasons, one of which they have a very rapidly growing internal market, and that they want to manufacture finished goods within their country rather than ship unfinished rare earth oxides to us.
The world wonders about the reasons for this export restriction. Is it because of environmental problems? Or are the Chinese simply flexing their muscles?
Ich will nicht ausschließen, dass die Produktion von seltenen Erdenmetallen an diesem Beispiel sei.
I don't want to rule out that the restriction of rare earth metal exports has something to do with the tightening of environmental regulations. But it almost certainly has also got something to do with China's power over the world market. I'm certain about that.
Da bin ich der festen Überzeugung.
So far, China's forte has been mining. But a lot of money can be made with processing, which is complicated and difficult. Right now, processing takes place in Japan, Europe, and the US. Many experts think that China also wants to control rare earth refining too. Soon, China could also dominate the market for processed rare earths.
Dass China zu 97% den Markt versorgt, liegt.
The reason why China supplies 97% of rare earth metals worldwide is because of cheap labor costs. Mining there is much cheaper than, for example, in the US.
Herauszuholen als beispielsweise in den USA.
We have become overly dependent on Chinese exports. Entire industries cannot function without rare earths anymore. Without them, the lights will go out, quite literally, because, for instance, energy-saving light bulbs contain rare earths. The governments of the US, Europe, and Japan have filed complaints with the World Trade Organization against China. and are making plans to look for new deposits around the world.
Da hat es aber auch noch geostrategische Bedeutung sicherlich.
Geostrategically, it makes sense to protect your own mines and not to ransack your own deposits. For example, the United States have their own oil wells, which they haven't touched yet. Instead, they bought oil on the world market. I would do the same. I wouldn't use my own supplies if I can get the same product cheaper on the world market. And it also makes sense to protect raw material deposits.
Bergisch Gladbach, Germany. China's restrictive export policy affects particularly those who need large amounts of rare earths for their daily business. Like the Magna manufacturing company Max Behrmann. The company founder once invented the magnetic fridge door. Today, the company mainly works for the automotive industry. A special magnet for each application.
We currently produce more than 50 different types of magnets for our customers. We produce 100 million magnets per year, which equals about 1,000 tons of material, including 50 tons of rare earths.
Nowadays, all modern high-tech magnets use neodymium and dysprosium. These rare earth metals ensure that the magnets are stronger and have a longer life.
The neodymium iron-boron magnets are used for sensors in windscreen wipers, interval switches, and in steering systems where they control rotational or angular movements. This makes driving more comfortable.
But expensive or failing supplies of rare earths make life difficult for the magnet makers.
Was wir hier spüren konnten, war, dass durch die Verknappung Spekulationen.
We noticed that the shortage triggered speculation. Prices for neodymium oxide rose rapidly. They exploded. They tripled, even quadrupled within 2 or 3 months. We had to shut down production and couldn't deliver on time.
Missed deadlines and exploding costs. The crisis hit the company hard.
Einige Projekte, die gerade angefangen hatten, sind gecancelt.
Some projects had to be cancelled. The industry desperately tries to avoid this dilemma of expensive raw materials and failing supplies.
What has happened to the magnet makers is happening to many other industries too.
The entire rare earth consuming industrial sector in Central Europe and North America is suffering from the twin problems of high prices for raw materials and a strategic dependence on a single supplier, in this case China.
Delitzsch, Germany. Right here in idyllic Saxony, an inventor tries to help the high-tech industry. Chemist Wolfram Palic is working on a method to recycle rare earths from industrial waste. He enters uncharted territory.
Here on this plate we have waste from the production of permanent magnets. Iron plays an important role, but also rare earths such as neodymium, dysprosium, and praseodymium. In principle, we're now trying to isolate these individual substances.
The magnetic waste is first heated in the blast furnace, the first step in the recycling process.
There are numerous types of high-tech and green-tech waste. We know that during the production of magnets, a lot of waste is accumulated, and we've just started to develop recycling processes for this waste. We separate the basic components to get pure, uncontaminated rare earth compounds, which can then be recycled back into the economy.
The recycling processes that exist today are usually only capable of extracting one valuable component from waste material. But Wolfram Pallich is not happy with that. He wants to recycle all the materials contained in a magnet.
It's not enough to just recycle gold from electronic waste, for example, if you then discard all the other elements. It
makes perfect sense. Instead of mining and processing rare earths with environmentally damaging techniques, we could simply recycle them from our waste. But the technology is still in its infancy and doesn't work for all rare earths. Pallich is currently working on a process for recycling the element neodymium.
We basically extract all the water here. This is done in a rotary evaporator. And here, in the case of neodymium, the dry substance undergoes a color change and goes from pink to blue. Now it's turned quite a nice blue. As a chemist, you always have something nice to look at. Good for your soul.
Here in the lab, the procedure is already working. But can Pallich make his recycling process work on an industrial scale? Could his method solve our commodity crisis? It's definitely the right idea at the right time. We all know that petrol cars are outdated. Electric vehicles are the future. But their engines need strong magnets with lots of rare earths in them.
When these devices are operating, they actually generate a fair amount of heat within them. Any inefficiency in the motor or the wind generator is realized as heat within the machine. And so they have to operate at temperatures much higher than one might expect when one talks about an electric car. And without dysprosium, this is not possible.
Dysprosium makes the magnets of electric car motors heat resistant, but it's expensive and environmentally damaging. Therefore, car makers would rather not use it. Ames, the United States. Here in the small university town of Ames in Iowa, Bill McCallum has set out to revolutionize the design of electric motors. His research is considered so revolutionary that the US government decided to get involved in the project. He and his team analyzed one of their latest magnetic compounds with an electron microscope. For the electric motor of the future, McCallum needs an entirely new magnetic compound that doesn't contain expensive raw materials.
Under current technologies, the magnets which are suitable for large-scale applications, meaning vehicles and wind energy, need to have dysprosium in them. Dysprosium is a heavy rare earth. The heavy rare earths are much rarer than the lights. Dysprosium makes up only a couple of % of the total rare earths in natural abundance in the Earth's crust. Yet in the magnets that we are currently using in electric vehicles, there's as much as 8 weight% of the magnet, and this is not sustainable.
To solve this problem, the scientists at Ames Laboratory are experimenting with new magnetic compounds. They would prefer to replace dysprosium with cerium because it exists in abundance. Unfortunately, the magnetic properties of cerium are quite poor. However, the secret is in the mixture. To start with, the compound is heated vigorously.
Dysprosium is a huge problem. It's a problem for the Chinese, and it's going to be a problem for the rest of us because we use dysprosium at a higher rate with respect to neodymium, praseodymium, the other rare earths, than its natural abundance.
The freshly mixed magnetic compound now has to be prepared for analysis. It's reheated and poured onto a rapidly rotating wheel. A vacuum prevents air from coming into contact with the compound and contaminating it. The result is an ultra-thin metallic band that breaks up into small pieces. These pieces contain only tiny amounts of the expensive element dysprosium. But the scientists still hope it makes for a strong magnet.
We really only take advantage of dysprosium at certain locations around the magnet itself. So if I have dysprosium at the very middle of the magnet, it's not doing me any good. It's wasted. So there are processes being developed to put the dysprosium only where it is required. So this can greatly reduce the amount of dysprosium that's there.
In the laboratory next door, the shavings of the new mixture are prepared for analysis. The ultra-thin metal strips are fixed on the specimen holder with glue. For Bill McCallum, every new compound is an attempt to get closer to the perfect magnet.
You all set over here?
Yeah, everything's ready to go. We're loading.
The search for the super magnet is a difficult process that takes a lot of time and money. However, the involvement of the US government shows that politicians too are starting to see the importance of such projects for our future.
This is a pretty good curve. Now we're seeing that there are various trade-offs that we can make, and we believe that we can really make materials where we have reduced the dysprosium or eliminated the dysprosium and reduced the neodymium and still have the performance necessary for use in electric vehicles.
The production facilities of the American sports car manufacturer Tesla. The small company only produces electric cars and doesn't use any rare earths in their motors. How is that possible? The secret lies in the design of the motors. They work without conventional magnets. Other manufacturers are now working on similar devices.
One of the things we're observing, or have observed over the last 2 years, and this was spurred by unstable, very high pricing from materials coming out of China, has been an effort by automobile manufacturers and other users to re-engineer their products away from rare earths. If the price for the magnets reaches a certain point, it's an invariant point and they're going to go to something else.
Just recently, a big international car manufacturer has started cooperation with a small Californian company. The idea? Getting rid of rare earths in all electric vehicles. even inexpensive everyday cars. Zero-emission cars, zero-emission power plants. Wind turbines are spreading quickly. In 2020, they will account for 6% of global electricity generation. This equals an output of 130 nuclear power plants. The problem? The latest large-scale offshore wind turbines are very powerful and require little maintenance, but they work with large magnets that contain huge amounts of rare earths. A massive problem for the environment.
In general, rare earths play an important role for alternative energy generation. You could say that renewable energy generation requires non-renewable raw materials, and rare earths are a prime example of that. A 5-megawatt wind turbine, for example, contains 800 kilograms of neodymium and 200 kilograms of dysprosium. In total, 1 ton of rare earths for a single 5-megawatt wind turbine.
The largest emerging market for wind power is China. Here too, manufacturers rely on rare earth metals for their turbines. The latest models need up to 4 tons of the valuable raw materials, a huge strain on resources. Würzburg, Germany. Researchers at the Fraunhofer Institute for Silicate Research are interested in the massive amounts of rare earths that are used in wind turbines and electric vehicles, but also in the tiny amounts found in computers and mobile phones. They see today's gadgets as tomorrow's raw material warehouses.
Wie intensiv werden im Augenblick die seltenen Erdenmetalle überhaupt aus dem Abfall herausgeholt?
How effectively do we recycle rare earths from our waste? We don't recycle them at all. This has something to do with the fact that in most devices, rare earth metals are used only in tiny amounts and in many different components. Our current recycling methods can only recover standard materials such as copper, but not rare earth metals. So we need to separate the different components first, and then concentrate them to get out the rare earth metals.
However, recycling complex devices such as mobile phones is difficult, because no one knows the basic materials they're made of, not even the manufacturers themselves. Many parts come from suppliers who in turn get their raw materials from other suppliers.
First, we need to know, what are the basic materials? Right now, we're building up a database for various consumer products, like mobile phones. We want to know, where is what? Once we know that, then we can start separating and concentrating raw materials to make recycling worthwhile. Currently, it's simply not economical to extract small quantities out of a big pile of electronic waste, like mobile phones.
With a scanning electron microscope, researchers hunt for even the tiniest amounts of rare earths. If we want to turn dirt into gold, we need to get down to the nitty-gritty. At molecular level, the discarded gadget reveals its hidden values.
Wenn die Produzenten begreifen, dass ich mit diesem Gerät auch
If manufacturers realize that they are wasting valuable raw materials, if they stop thinking about the money they get from simply selling products, then they will understand that this old device is a source for making new devices.
die ich wieder einkaufen muss.
Only then will we start to have a recycling economy.
Kreislauf hin, eine Wertstoffwirtschaft.
The Electron microscope shows the basic ingredients of a device. The grey patches indicate rare earths. The computer only takes a few seconds to find out what the small grey spots are made of. They contain neodymium and dysprosium, valuable rare earth metals. But it's still a long way to the recycling process.
Europa hat sicherlich eine riesige Chance in dem Recycling.
Europe certainly has the chance to lead the way in recycling. We need these raw materials for our economy. Our industry needs it. But our countries are poor in natural resources. On the other hand, we've developed recycling methods in the past, so we aren't starting from scratch. And I think this is our chance. I'm not only talking about recycling rare earth metals, but about recycling all materials, including copper and aluminium. I myself am working on recycling the raw materials from old waste disposal sites. We're pioneers in this field, and it's a huge opportunity for Germany and Europe.
Wir als Bürgerinnen und Bürger, wir als Nutzer eines Gerätes müssen wissen,
We as citizens and as consumers need to be aware. What is actually in the products we use? What is their commodity value? When we look at household waste, we often discover more than 10 or 20 mobile phones in the rubbish. Usually they're simply incinerated. But this is wrong. This is no longer sustainable. A cell phone is like a mine. We speak of urban mining. And we do need to recycle it. This is important. Recycling is only economically viable if prices for recycled raw materials are lower than the prices for primary raw materials. At the moment, this isn't the case. So we're now developing technologies that will be used in 5, 10 or 15 years. If commodity prices continue to rise, it'll be profitable one day.
Dann wird es sich lohnen.
The Americans have reopened Mountain Pass, which used to be the world's largest rare earth mine. Rising prices on the world market drive the project, and the prospect of independence from Chinese suppliers. The investors hope for a 15 to 20% global market share and stable prices. They use sophisticated technology to protect the environment. The mining company promises to use cleaner processes in the future than in the past, and still hopes to be cheaper than the all-powerful Chinese competition.
In the processes that have typically been used in China, they use acids that are so aggressive that they chew away on the thorium oxide that's present, and it literally goes in solution. So for instance, if you take sugar and you put it in water and it disappears into water, that's dissolving or it's going into solution. So these strong chemicals will do the same thing with thorium, and the thorium ions go in solution. Then it becomes a wastewater problem, and it can leak into the groundwater and contaminate it. In our system, we've redesigned our chemistry such that we avoid the dissolution of the thorium. So it stays insoluble, and it stays as solid, and then we just pull the rare earths away from it. And it took a while to figure out how to do that.
rare earths. However important they may be for the future of our modern technologies, their environmental problems are hard to control. Yet many experts believe that these difficulties can be overcome.
So our goal is to be the true rare earth innovator in the world, the key, the most innovative company out there. So we're going to continue to be looking for new platform opportunities and trying to stand these things up as quickly as possible.
But still, aren't all those tons of rare earths used in electric cars and wind turbines exacerbating the environmental problems they're supposed to solve?
Zumindest im Augenblick überwiegt der Nutzen.
At least for the moment, the benefits outweigh the detriments. Obviously, we have to do everything we can to keep it that way. So we must work hard to ensure that the use of these elements doesn't have any adverse effects.
Nicht letzten Endes zu negativen Folgen führt.
We all know that the supply of raw materials is dwindling. We need to start thinking in circular flows of potentially recyclable resources. Only then can we really take advantage of the benefits of rare earths.
Wir reden mit Politikern, wir reden mit Industrievertretern.
We talk with politicians. We talk with industry representatives. We talk with the EU Commission. And things start to change. 2 or 3 years ago, people thought you were a fool when you talked about the commodity crisis. Today, everybody talks about it. And everybody talks about rare earths. Just like we need a more sustainable approach for producing our food, we need one for sourcing our raw materials.
Müssen wir es halt auch diese Rohstoffe als Lebensmittel tun.